All right, so moving on with 15.6. Now we can look at a spherical shell of charge. And so we're going to do this mostly conceptually because the better proof of the formula comes from something called Gauss's law, which we need to build to a little bit more in terms of our knowledge. But let's take another look so we can understand why we've been using the point charge formula with a little bit more details. So if we've got a spherical shell of charge with radius r, and it would have charge q, make it positive, why not? So you would have r would be the radius, and we could be observing inside the sphere, or we could be observing outside the sphere. So in the case of looking at outside the sphere, what we have been doing is saying that it acts like a point charge. And so the field would be going out in all directions. So we're just looking at one spot here. And then we've been saying that inside the sphere, that E is equal to 0. And so let's go about thinking about this conceptually. So we'll take our sphere, and we're going to go ahead and do that outside observation. So here's our R, and we'll cut up our sphere 1, 2, 3, 4, 5. Oh my goodness. Let me try this again. Okay, 1, 2, 3. I keep adding more slices than I mean to. Okay, fine. 4, 5, 6, 7, 8. Okay, so let's think about all these contributions. So the contribution from 1 is going to be in this direction, so E1, and then I'm going to do on axis in orange and everything else in blue. You'll see why in just a moment. So this coming in here, so we would have E2, and then we could see that E2 sort of corresponds to E8, and then we could have E3 coming down here, which sort of corresponds to E7, and we could have E4 coming in like so, which would then correspond to E6. We can see these are all canceling each other out. And then the contribution from the other side of the sphere, a little bit smaller, E5. And we can see that the only field that we have left is coming directly out from this location. So this is why it just radiates out uniformly in all directions. Conceptually, of course, if you want to do the integral for this, it's a little bit involved, but it's in section 15.10. And like I said, the more beautiful and exquisite variation of this will come from Gauss's law. And by the time we get there, it's like 3 lines. It's so beautifully simple, but we've got to earn that by doing a little bit more physics. So anyways, conceptually now we've kind of seen why it acts like a point charge outside. Now let's build on this. So we've said the E sphere outside is 1 over 4 pi epsilon naught q over r squared times r hat, where r is bigger than r. And then we've said that it's 0 inside. Where Q is the total charge and R is the radius. Okay, and of course the magnitude would be 1 over 4 pi epsilon naught q over r squared. Okay, so it looks like a point charge, and it behaves like a point charge, which is the beauty of Coulomb's law, but let's go inside the sphere now. So inside the sphere, if we were to look at a point inside the sphere, we would see that it would have a charge from this side, and then 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 this side, and essentially everything cancels each other out. So all the contributions add to 0. And again, we'll see a better proof of this with Gauss's law, but for now you can sort of visualize this. Now, it's important to note the electric field is not always 0 inside a sphere, but it will never have a non-zero contribution from the sphere itself. So, for example, if you've got a sphere, the net field is going to be 0 because the only thing that could be contributing is the shell itself, which is 0. However, if you were to take the same sphere and then put a little point charge outside, this would be contributing a field that would go through that sphere. But the only net field there would come from the charge, not from the shell itself. So it would be E net, not 0. So there are some implications. So that means that a uniformly charged plastic ball that charges on the surface do not polarize. So in this case, if you've got your charged surface on a ping pong ball, the ping pong molecules don't polarize because the surface charges would contribute to a 0 field. Or likewise, if you had a plastic ball surrounded by a metal ball, the metal ball would not polarize, and this metal ball was charged, the metal ball would not polarize the inside plastic ball. Also, if you have a solid metal sphere, the excess charge, so solid metal spheres essentially act like charged shells. The excess charge goes to the surface, and inside there is no excess and no field. Okay, so moving on to a solid sphere charged throughout its volume. So we've looked at charge distributions throughout the surface, but you could look at something that has a charge throughout a volume. There is a natural occurrence of this, so a nucleus is packed with protons and neutrons. So you have a solid sphere of uniform charge, so for example, and in this case the radius is 10 to the minus 15 meters. So we've got this uniform charge throughout a sphere. The electron cloud also has uniform charge density. So this is something that exists in nature. You could also synthetically produce it. So let's look at how to analyze this. Okay, so when you've got a shell of charge or a sphere of charge, you can model it like there's several charged spheres. Now, outside a shell of charge, it's pretty straightforward. So if we're someplace outside, positive maybe, then the electric field would be pointing out. It's going to act just like a point charge. And we can just think that through. So in that case, E is equal to 1 over 4 pi epsilon naught Q over R squared, where R is greater than the radius of the shells. Now, if we go inside, it gets a little bit more interesting. So go ahead and start a new sheet. Inside, we would have a series of shells. So let's say we're observing with R right here. Okay, so if we think about this conceptually, these shells outside of it will contribute nothing because they are outside. We've already determined that that's going to be a net contribution. However, all of these shells here, we are outside of them. So they are going to contribute to a field. So we're going to have an ever increasing electric field as we go from the center all the way out. So E net outside shells is 0. Inside shells, not so much. So we need a way to add them all up because that's been our approach all along. So E is equal to 1 over 4 pi epsilon naught delta Q over R squared. And we're looking for each inside shell. So now we need to find delta Q. And we need to find it as the fraction of the total charge. So delta Q is going to be equal to the total charge Q times the volume of inner shells divided by the volume of the sphere. So this is equal to Q 4/3 pi R cubed divided by Q 4/3 pi big R cubed. And if we put it all together, E is equal to 1 over 4 pi epsilon naught Q over R squared 4/3 pi R cubed over 4/3 pi R cubed is equal to 1 over 4 pi epsilon naught Q over R cubed times little r for R less than R. So as we hinted, as this gets bigger, the amount of charge inside gets bigger, so the field gets bigger. And so the larger volume, V is proportional to R cubed, compensates for the 1 over R squared dependence. And we can also see that E is 0 at R equals 0, so at the center it's 0. And in the special case where R, little r, is equal to big R, we get that E is equal to 1 over 4 pi epsilon naught Q over R squared. And that wraps up chapter 15.